So now we're going to move into discussing some relaxations of differential privacy. The first one, epsilon delta differential privacy, is sometimes referred to simply as relaxed privacy. So what is it, and how does it compare to our previous definition? This is the change. So we have our multiplicative requirement, but we have this little escape hatch over here. That's all. Typically, we assume we are interested in this for the case that delta is sort of cryptographically small. So delta is very tiny, or should be very tiny. Great. So our original definition of differential privacy is just epsilon 0 differential privacy. We just set delta to 0 to get rid of that term. Okay. Good. So now I want to define the privacy loss random variable. So it has some icky notation. We have a pair of adjacent data sets, x and y, and we think about what happens when we run m on input x. And we look at, remember I have fixed x and y, so we look at, for the output that's produced when the database is x, the log of this ratio. That's going to be our privacy loss random variable with respect to y when we're running on x. And we sample this privacy loss random variable, as I said, by run m of x to obtain xi and then output that quantity. All right, privacy loss random variable. With that in mind, we can say that epsilon delta differential privacy promises that with probability 1 minus delta, the privacy loss will be at most epsilon. This is not really obvious from the definition, and it requires proof. We won't go through the proof today. So why do we care about this? What do we gain from this relaxation? Well, we gain many things. For example, we will see better composition bounds than we had before. We can use cryptography to simulate a trusted center, where the escape hatch delta is going to be the probability that the adversary breaks the crypto system, for example. You can prove that in the two-party case for differential privacy, which has to be defined, but basically one party has a value A and the other one has a value B, and they're trying to compute some function of A and B. You can prove that cryptography lets you provably achieve better accuracy in the two-privacy case, or rather epsilon delta gives you better accuracy than epsilon 0. You can live with perhaps some tiny cryptographically small probability of a complete privacy breach. As I said, this like little escape hatch. And that lets you do some things that you couldn't otherwise do. And finally, we were talking about adding Laplace noise for our real valued functions. But many people who work with data immediately say, well, how about Gaussian noise? Everybody understands Gaussian noise really well. They understand the high-dimensional Gaussians. There are a lot of reasons for wanting to do it. It's more tightly concentrated around its mean and so on. So when we relax to epsilon delta differential privacy, we will be able to use Gaussian noise, and that's going to help us a lot in accuracy. Yes?
So delta is negligible?
I want delta to be negligible.
It's different from epsilon.
Correct. Epsilon we think of as a small constant. Right. Yeah?
I'm confused about the use of cryptography. So where does cryptography or hardness...
So I wanted to use crypto to simulate a trusted center. All right, so we'll use multi-party computation to do everything that the trusted center would have done. There's some chance that the adversary will manage to decrypt and break privacy. It's a small chance. It's negligible, but that's the delta. It's that that tiny probability of distinguishing. Gaussian noise also permits some incredibly cool geometric algorithms that was shown by Nikolov, Talwar, and Zhang. So today, I'm going to try to talk about these three things in blue. Start with composition. So I've been a little hand-waved. Yes?
Epsilon, privacy, you said that epsilon sort of is a notion of how much privacy is lost.
Yes.
Is there some sort of a concrete intuition for that? In some sense, like after X number of queries, the adversary will learn a lot, or...
Well, we know from the composition bounds, for example, that for the original one that I mentioned early on, if our algorithm is epsilon differentially private for one query and we run it for k queries, it'll be k epsilon differentially private. When k epsilon gets uncomfortably large, that's privacy loss. But you can also flip it around and say, if you want your cumulative privacy loss to be epsilon, then run each of the individual queries with privacy loss epsilon divided by k, and when you sum them up, you'll get at most epsilon. That will give you less accurate answers on the individual queries, but your cumulative loss is good. What we're going to get now by the relaxation is, well, as the slide says, we're going to end up paying something like root k rather than k.
Just the quantitative value of epsilon, is there a way, like if epsilon is 2, like does that have an intuitive notion?
Wait till the very, very end of the talk, and if I have an ask again if there's time. Okay. So, okay. So we need to say really, how are we formalizing composition? I've been kind of hand-wavy about it. Beyond multiple queries to the same database, I'd like to be able to handle multiple adaptively and adversarial generated databases and mechanisms. Let the adversary generate the pairs of adjacent data sets, for example. I'd like to answer questions of the following form. Bob goes through life. He gets involved in, say, 10,000 databases. If he were to have a lifetime privacy, cumulative privacy loss of epsilon equals 1, what should be the value of epsilon prime that is guaranteed for each of the individual databases? So composition, we want to be able to answer that. Quantitatively, we're going to get a bound that looks like this. For all delta prime, the k-fold composition, after we define it, of epsilon 0 differentially private mechanisms looks like this messy thing. We're going to talk about this messy thing a lot. But for now, let me just observe the following. You can think of it this way. Think of this as an expected loss. Think of this as a standard deviation. And so what we're saying is the probability that we're going to be t standard deviations in loss away from our expected loss is exponentially small in t squared. Okay. And when you optimize in here, it turns out what this gives you is that your cumulative loss looks something like square root of k times epsilon rather than k epsilon. Now there's got to be a delta in there, and that delta is going to show up here as a multiplier of log of 1 over delta. So here's how we formalize things. This is like the left-right game of Bellare and someone remind me. You guys must know. All right. Anyway, so we are going to play a game in which, let's say, a curator is going to first flip a coin, get a value of 0 or 1. And then the adversary is going to do the following. The adversary will present to the curator a pair of databases of the adversary's choice. This is the first pair. That's why the first index here is a 1. And a mechanism M1. The curator, who has fixed B once and for all, will run M1 on the chosen element of the pair. And that's what the adversary gets to see, that outcome. based on that, the adversary can choose a new pair of databases and a new mechanism, and then our curator will run the new mechanism on the selected element, same B. Sorry. Same B, and so on and so forth. And the job of the adversary is just to figure out what B is. Okay? So for example, when B equals 0, maybe this is the real world, and when B equals 1, we've gone through and replaced all of Bob's data with junk. And the adversary's job is trying to figure out which of the two is the case. Or I like to think in terms of people and ghosts. And the adversary is trying to figure out if Bob is a person with real data or a ghost who has no data. Okay, so for the epsilon 0 case, the proof of composition relies on this fact that we prove that if the privacy loss is bounded by epsilon for epsilon less than 1, then the expected loss is bounded by epsilon squared. Remember, epsilon is less than 1, so the expected loss is much smaller than the worst case loss. So then what we do, sort of following along the lines of these evolution of confidence arguments in earlier work, we model the cumulative privacy loss as a martingale. So we have a bound on the maximum loss. If it's an epsilon differentially private algorithm, the bound on the maximum privacy loss is guaranteed to be epsilon always. And we have a bound on the expected loss, which we prove. And let's call the first quantity A and the second one B. And we apply the Zuma-Höfting lemma using the fact that the privacy loss at each step is an independent bounded random variable. And we get that the probability that the cumulative loss is off from its expectation, this is linearity of expectation, is at most the probability that this difference exceeds z times the square root of k times the max loss is bounded by e to the minus z squared over 2. I'm not going to go through that proof, the proof of the expectation, but I did choose to put it into the slides, for one thing, so that they're there for the record, that anybody can see them, and also to note that we're really looking at a KL divergence notion here, where U is the distribution on outputs when the database is X, and Z is the distribution on outputs when the database is some adjacent to X prime. And so then we end up proving something about the KL divergence of two distributions that come from the running of a differentially private mechanism on adjacent data sets. And that's the whole proof. You can see it's not very long, and you can look at it. And Guy and I recently managed to get rid of that factor of 2, which gives us actually the right answer for randomized response. Okay, now, what is it? Oh, and just let me mention that the argument when delta is not 0, first of all, the statement of the theorem is the same, except we have k times delta here. So the deltas are adding up. And the argument is essentially the same as the argument I gave you, and it uses that fact that I stated earlier, that one interpretation of epsilon delta differential privacy is that with probability 1 minus delta, the loss is bounded by epsilon. Okay. Now, here's a serious algorithm. It's called the sparse vector algorithm, and it has proved to be extremely useful. And this, I guess, will be the one real proof in the talk. So we have a database of size n. And we're looking at a collection of queries, k of them, and k could be very large. And unlike the case with the small DB algorithm, where we use the exponential mechanism to choose a small database, in that case, all of the queries were known in advance, but here the queries are going to be presented in an online fashion. Now, these queries are going to have a certain property. That is, at most, some number C of them, not too many, are going to be said to be significant, meaning that the value of the query when evaluated on the data set, significant means that that value exceeds some fixed publicly known threshold T. And we can always enforce this behavior by keeping track of how many significant queries we've seen and just quitting when we get up to N or C, whatever the bound is. So this is what we're going to have. And the goal will be to find and optionally release values for significant queries and pay only for the significant queries. So we may have tons and tons and tons of insignificant ones, but just a couple of significant ones. And so what's being produced is, as output is, insignificant, 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 significant, insignificant, insignificant. So that's what's being produced, zeros and ones, insignificant for 0 and 1 for significant. So the way we're going to solve this problem is we're going to first build an epsilon 0 differentially private primitive that will halt when it has one significant query. So in this example, it'll run in here, and it'll stop when it hits that first significant one. And then it will run it again, and it'll stop here. And then we'll analyze the cumulative loss using the composition theorem. So here's our basic algorithm. T is that publicly known threshold. We're going to add noise to that threshold, scaled to 2 over epsilon. And now we're going to do the following. For each query, we're going to compute fi of x when the query fi is presented. We're going to add some nice random noise, and we'll see if that noisy value exceeds the threshold. If so, we'll output 1 and halt. Because remember, this is the little building block where we're going to halt at the first significant query. And otherwise, we'll output 0 and repeat. So is it clear what the algorithm is?
I'm sorry, what's your goal? Just the goal.
The goal is to identify the significant queries as long as there aren't too many of them.
But I mean, you can do it perfectly, right? So the reason of adding noise,
we want to do it with differential privacy. So we are first going to build our little epsilon 0 differentially private primitive. That's this. We're going to argue that it's epsilon 0 differentially private. Then we'll apply composition.
Utility is measured how far is the limits of the variable?
Utility will be measured as follows. If you're far from the threshold, then you must give the right answer. You want to give the right answer. If you're close to the threshold, maybe you'll give the right answer, maybe you'll give the wrong answer. So utility is captured by the definition of close, and that we will call alpha. So consider some length k output. We're going to run this thing until it hits the first significant query. Suppose that happens to be the kth query. So what does the output look like? It looks like k minus 1 zeros, indicating that the first k minus 1 queries are insignificant, followed by a 1, indicating that the kth one is significant. So we let g of x be the maximum over the insignificant ones of this value. So we're going to fix all of the random values except the kth one. And we're going to define g of x accordingly. So this is, I'm assuming that each of my individual functions, fi, has sensitivity 1, so g of x will also have sensitivity 1. So what is the probability when the data set is x that we actually produce this string? That's going to be the probability over the noise that we introduced for the threshold and the noise that we've introduced for the kth query, having fixed the noises for queries 1 through k minus 1, that we get this behavior, which is just plugging in from the algorithm. It's the probability that the threshold that we chose was bigger than the max of everything from 1 to I minus 1 plus its noise. And when we add noise to the kth one, we exceed the threshold. That just says, this says we produce zeros on the first k minus 1, and this says we produce 1 on the kth. So just rewriting, that just says that t hat is in this interval. Now, if we write this out, this is, we're going to integrate over the noise value for the kth query and the noisy value of t hat. It's the probability that we got this noise times the probability that we got this value for t hat times the indicator function of that t hat is in this interval. That's exactly what that said. Okay. Now let's call this quantity star. Then we define a change of variable. So what do we have going on here? We have a change of the max, and we have a change of what happens on the kth query. And these could go in the wrong directions to make things bad. So we define these new variables, we apply the change of variables, and we get this. Just trust me, it's true. This is from the previous slide. So when we take these together, what's going on here? Well, I'm going to take the probability that we got v hat here and replace it by e to the epsilon over 2 times the probability that we got v. And notice that v hat minus v is bounded by 1. So we used noise according to, sorry, it's got to be bounded by 2 if I wrote that. So we used noise that was bounded by Laplace 4 over epsilon, so we'll have a privacy loss of at most epsilon over 2. Oh, right, sorry. This is why you have a 2. You get a 1 from here and a 1 from here. And for the other term, again, this is at most e to the epsilon over 2 times that, because t minus t hat has a difference that's bounded by 1, and we used Laplace noise 2 over epsilon. So when we plug that in, we get this. And this is this actually concludes the proof. We started with the probability that a of x was equal to a, and we have here the probability that a of y is equal to a, and they're different by this multiplicative e to the epsilon. Okay. So what happens under C-fold composition? Well, if we used simple composition, we would get something like this for our accuracy, which has a C out here. And if we use epsilon delta differential privacy, we get this square root of C times the log of 1 over delta. Good. So what do we use this for? Well, the most fantastic use of it is due to Hart and Rothblum. And they want to handle a lot of counting queries, and they want to handle the case where these queries are coming online. So what they do is they take the ordinary multiplicative weights update algorithm. I guess it was due to Plotkin, Schmois, and Tardosh, and they're going to have sort of one expert for each element in the universe of possible elements, and they're going to essentially learn an approximation to the database. So they're going to represent the database as a histogram for all of the different kinds of people in the universe. For each kind, how many people of this kind are in the database? That's the count, the histogram count for that particular cell in the histogram. So you maintain a public distribution D on the universe, which is initially uniform. And when you're presented with a query, you first look at the value of this query on this public distribution D. And it's going to give an estimate of Fi of x, the secret database. Now, maybe it's a good estimate. Maybe it's complete crap. We don't know yet. If it's a good estimate, meaning that the absolute error is less than some amount t, then great. We just say, hey, you already know the answer. Evaluate it on that public distribution. And if it's not a good estimate, we're going to add some fresh noise and release an approximation to Fi of x and invoke the multiplicative weight update rule on the public distribution. And of course, these two lines in blue, they can be done by the curator, they can be done by the person who's using the data set. You don't need any secret information to do the parts in blue. So what's going on in black? What's going on in black is basically sparse vector. Oh, you have a value that exceeded a threshold. Hello. And when that happens, you just do a simple counting query. You get the outcome, and you proceed. So sparse vector lets you implement this. So what happens here? We get down to what happens with private multiplicative weights. If you did simple composition, then you would get a bound that is similar to what you get in the BLR, Blum, Liggett, and Roth algorithm. But if you use epsilon delta differential privacy, you get an error that looks like this. And the key point, and I'll talk about that more in a moment, the key point is that, and what Hart and Rothblum show, is that the number of updates, the number of significant queries, it looks only like like n. And so that square root of c becomes a square root of n, and that shows up there. What this turns into isn't, okay, this is the absolute error bound. And look at what happens when you have a universe where each element is a much less than n squared dimensional object. We're looking at the fourth root, so we end up with square root of n here. So we have a square root of n here and a square root of n here. That's big. That's an error that looks like n. But if you have the log of the universe size, the number of attributes much less than n squared, then you get meaningful answers again. And that's kind of the best you can do. So there's a very discouraging result of Bunn, Ullman, and Vadan, which says that any differentially private algorithm that accurately estimates d fractional attribute means. So these are basically one-way marginals. Requires at most has to have a number of data records that's smaller than square root of d. Okay, and the proof uses fingerprinting codes, which were introduced by Bonnet and Shaw in the context of traitor tracing. So we're back to traitor tracing. And the particular codes that they're using are due to Gabor Tardos. But this business of just asking for attribute means, especially when you're using the fingerprinting codes of Tardos, gives a distribution on databases that's extremely natural. And that makes me unhappy, of course, because I don't want negative results for very natural sets of queries or natural sets of databases and queries. So this is bad news. It's just plain bad news.
But impossibility results is just to show you that you have to do something else around the impossibility result.
This is an unconditional result. It's.
So you think this is really inherent and there is no way?
Yeah, on the other hand, okay, so here's an interesting question. Is it the case that we expect the dimensionality of the data to look like the square of the number of records in the database? There must be lots of interesting settings in which data are plentiful, and that is not the case. When you have zillions and zillions of records, you would need zillions and zillions of attributes squared. Zillions and zillions squared of attributes. On the other hand, it's kind of interesting. I was reading a report from the National Research Council on, I don't know, the challenges of big data or whatever. And a few times in this report, which has a stellar set of authors, there was a reference to the assumption or the belief that the number of attributes grows linearly with the data set. Linearly, not quadratic. I want to investigate that further. I read this fairly recently. But, certainly you can think of cases where the data dimensionality is huge, like genomes. So, okay. Another application of epsilon delta differential privacy, as I said, is that you can add Gaussian noise rather than Laplace noise. And the theorem looks like this. This is our old theorem, which said that to achieve epsilon 0 differential privacy, you can add noise that's scaled to this L1 norm difference sensitivity. And for the Gaussian, you get to look more like the L2 norm. So to achieve epsilon delta differential privacy, you can add noise that's normal with this variance. Remember that this is the square of the standard deviation. So you end up with delta 2 square root log 1 over delta as the expected size of your noise. So for k arbitrary counting queries, the L2 sensitivity is much smaller than the L1 sensitivity, and it's a big win. And it's also similar to what we get under advanced composition. And that is perhaps not an accident. So just bear with me for a second. Just think about one-dimensional Gaussian, because for high dimensions you can reduce it to the one-dimensional case using the spherical symmetry of the distribution. So suppose I'm adding noise that's drawn from a Gaussian with variance sigma squared. And I want the privacy loss to be bounded by epsilon. So I look at this ratio. This is what happens when the database is X. This is what happens when, at the worst case, when this is some neighboring database Y. And when we grind this through, we get that this quantity is less than epsilon. Basically, whenever the draw has the draw from the noise, sorry about that, calling it X, is bounded by sigma squared epsilon over delta F minus delta F over 2. Great. So using standard tail bounds, we can ensure that this thing is met with probability at least 1 minus delta when we take sigma squared to have this size. Now, let's just take a closer look at this. Let's not put that square root log 1 over delta term into the standard deviation for our noise and see what happens. So it's just plain, oh, no, forget that. Anyway, let's look what happens. As long as this is the case, the privacy loss is bounded by epsilon. What happens outside this range? We don't necessarily get death and destruction. Probably our draw from the Gaussian was just a little bit larger because the Gaussian is very tightly concentrated around its mean. And so most likely what happened to us was that our privacy loss, instead of being potentially infinite, is simply 2 epsilon. And in general, we can argue that for the Gaussian, the probability that our privacy loss is at most t epsilon is going to be something like 1 over t e to the minus t squared over 2 for all t. In other words, when you're using the Gaussian, the privacy loss random variable is itself a Gaussian, which is really cool because we understand it very well. We understand its behavior under group privacy very well. It's tightly concentrated around its mean. So you might remember the form in which we expressed the composition bound. We looked at the probability of being t standard deviations away from the mean. And we said that that was at most e to the minus t squared over 2. And so this is very, very similar. T standard deviations away, t epsilons away, e to the minus t squared over 2. Very similar. So this suggested a new characterization of a kind of privacy, which we call concentrated differential privacy. And it has two parameters. It has a mean mu, and it has, a standard tau. And the guarantee is something like this. The probability that your privacy loss is more than t taus away is bounded by e to the minus t squared. Formally, what we show is that when we subtract away, the way we characterize it is by saying when we subtract away the expected loss, what we are left with is what's called a sub-Gaussian random variable with standard tau. And the existence of a tau that satisfies this for the moment generating function is what defines a sub-Gaussian random variable. So the nice things about this are, first of all, it's more relaxed than epsilon 0 differential privacy. Epsilon 0 says with probability 0 your privacy loss exceeds epsilon, and as we know, the expected loss is still epsilon squared, at most epsilon squared. What we have now is that still the expected loss is at most epsilon squared, but, well, these sort of graduated claims about the chance that you're way far away from that is very small. So it's a more relaxed notion. It has nice group privacy. And interestingly, if you look at the behavior under composition of concentrated differential privacy and epsilon 0 differential privacy and also epsilon delta, it's all the same. So if you're doing many, many studies, you can be much more relaxed about each individual study and use concentrated differential privacy instead of the pure or the epsilon delta, often. Okay.
Is there some simple, you showed one mechanism, but is there some simple mechanism that right away achieves this concentrated differential? So this Laplacian doesn't because it's specific to this epsilon.
Actually, any epsilon 0 differentially private mechanism is epsilon squared, comma, epsilon concentrated differentially private. And also the Gaussians are. And so anything that you build by combining those things, any complicated analysis that you build by combining those things, you can apply the composition bounds that come naturally for the sub-Gaussians and stay in this concentrated form.
So you're saying it's more like a convenient just property, but the notion of epsilon differential privacy already implies this for the analysis, or this has, there is a benefit of analyzing directly this notion as opposed to epsilon differential privacy? Because this looks like a more kind of gradual.
It's all I can say. I don't think we totally understand, but what we do know is it's more relaxed. It should be more flexible, and the way to think about it is not for any individual mechanism, but some complicated analysis that's a combination of little mechanisms.
So it lets you add less noise.
By being more relaxed and less demanding, you can get away with better accuracy, right? Okay, another thing that we like about epsilon delta differential privacy. Suppose we have a data set and we'd like to release an estimate of its median. So for nice distributions, this is typically very stable. If there's, okay. But maybe the data don't look at all like they come from a nice distribution. And this could happen for two reasons. One is they don't come from a nice distribution. And another is they come from a nice distribution, but this was an incredibly weird draw. You were just very, very unlucky when you created your data set. So here's an example of a data set that is really bad with respect to the median. When this yellow point is over here, this is the median. If the yellow point moves over to the left or anywhere in here, this will be the median. So this is bad. The sensitivity of the median is big in this case. So what propose test release does is it's a way of trying to be able to scale the noise to what Nisim Raskolnikova and Smith called the local sensitivity for the median, which is the sensitivity of the median on this particular database. And they had one way of achieving something like this, which they call smooth sensitivity. And what Jing and I did is come up with basically a technique that lets us have a quick and dirty way of doing this. So the idea is that, for example, you could propose a local sensitivity, and then you can run a differentially private test that says how far is this data set from one whose local sensitivity is bigger than S. This is a sensitivity one query, right? If this database is 25, the addition of 25 different nodes away from something whose local sensitivity is bigger than S, then a neighboring database will be at most 26 away. So we can ask this question, and if the response that we get back says, oh, you're really far from a nasty data set, then we just add noise that's scaled to that to S, and we're fine. Now, if the noise was super weird, like, in fact, this data set has bad local sensitivity, it is distant 0 from one whose local sensitivity is bigger than S, but the response comes back, oh, it's very large, because when it did the draw from the Laplace mechanism to answer this question, it just got a really bad result, really big positive result. So that's a super weird noise case. I will call this delta of the nasty kind. And we're screwed. Maybe there is death and destruction. So this is one of the reasons we want delta to be cryptographically small, of course, so that we don't fall into this. So these guys do not give concentrated differential privacy. This is the nasty version of epsilon delta. But of course, as cryptographers, we're generally quite comfortable with the idea of cryptographically small probabilities of failure. Okay. Now, I don't remember what else is in this talk. I'm going to mention this work. So far, most of the time we've been talking about data sets where the curator had our hands on all of the data and then answers questions. Sometimes the questions are presented as a batch, sometimes they're presented in an online fashion, but that's what's going on. But of course, in real life, you might have other settings, like streaming settings. So here we introduce the notion of differential privacy under continual observation. So basically, we're going to look at algorithms that produce observable outputs at every step. And the most natural of this is a counter. So you say, I don't know, maybe you're counting visits to a website or something. So you separate time into chunks, and you want your user to be able to estimate at any time how many times the website was viewed cumulatively in slots 1 through I. So here's our what's going on. You have the algorithm, it has some state, it sees the first input, it moves, produces an output, moves. This must be your animation from a million years ago. Okay, and so on.
I'm going to flip a coin and give you an answer.
No, I didn't know how to make things move yet. Okay, so I'm going to describe one kind of privacy guarantee that you might want to make, which we call event-level privacy. It's very, very important to specify your granularity of privacy. For example, if you're creating a movie recommendation system, do you want to protect all of the movies that Guy watches or just one of them? Right? Any individual movie that he watched you might have privacy for it, but if there's a general theme, you might be able to detect it. Event level is only promising tiny granularity privacy, not everything that somebody might do. Okay, and you can I'm just using this as an example for this particular algorithm. So to capture time, maybe we can augment our universe with a symbol of bottom. So we would just say that two strings are adjacent if there is a W. I'm sorry. Forget that line. Just forget it. If there is a W in the universe, so that tau can be obtained by replacing one occurrence of W in sigma by bottom or vice versa. So I want a non-bottom element here. So these guys are going to be defined to be adjacent inputs, neighboring inputs. Okay? So here's a counter. What we're going to do is we're going to maintain counters for all intervals of length powers of 2. So if this is time, here are the time intervals. This is the interval consisting of the first step, the second step, the third step. This interval is the first 2 steps, the second 2 steps, and so on and so forth. And at the end of an interval, we're going to add, so whenever we get a completion here, we're going to add some fresh draw from a Laplace distribution with the appropriately chosen parameter and publish the result. And at any time I to find, to answer how many ones there are in the count in steps 1 through I, we're going to find a union of at most log total time is t, disjoint segments, whose union is that interval. And we can use the binary representation of I to do this. And we just add noise that's scaled to the log of t over epsilon for privacy. And then by a Chernoff style bound, we get error that with high probability will be at most something like log to the 1.5 t over epsilon. And in this version, we needed t in advance, and I think Dawn and her co-authors have a version where you don't need t in advance, correct? Okay, so in general, there's a really rich algorithmic literature for differential privacy. There are also a lot of negative results and complexity-related results, and but here's an example. Here's some examples of the kinds of things that people know how to do now. A lot of data analysis tasks. And there's also a book that Aaron Roth and I wrote, which is available legally for free and on the web. So take a look. But, of course, differential privacy cannot be a panacea. The fundamental law that said overly accurate estimates of too many statistical queries is blatantly non-private, that still holds. It's a fundamental law. I told you about it before I told you anything about differential privacy. What we know is that, say, concentrated differential privacy can let us match at least one instantiations of this law. So it's as good as the law provides. But in general, there are open questions for various kinds of queries. But it is not a panacea. So in my last few minutes, I want to talk about some applications of differential privacy that actually have nothing to do with privacy. None whatsoever. So this is differential privacy in the service of other goals. Here's a paper by Malesh Pai and Aaron Roth. And it's about algorithmic mechanism design, not our kind of mechanisms, but the economics kinds of mechanisms. And they point out that differential privacy provides a powerful toolkit for controlling the stability of mechanisms in general, which yields a set of tools for designing novel mechanisms, even in economic settings, completely unrelated to privacy. So this... Another example in game theory. This is a brand new one. Differential privacy offers just the right tool. It requires blah, 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 blah. They use just the existence of a differentially private algorithm for, in order to argue whatever it is they argue. So this is the fact that there exist differentially private algorithms that are now having implications in game theory. And I'll tell you about one more application, which we call correctness protection in adaptive data analysis. You've probably all heard of the paper that most published results are false. And there are a lot of efforts to control false discovery in science. There's famous Benjaminian Hochberg's algorithm and a huge literature that followed from that for controlling what's called the false discovery rate in multiple hypothesis testing. I assume that you all have an intuitive idea of what this is, but these are the results that sort of falsely say, I don't know, drinking coffee is really bad for you, when in fact it turns out to be really good for you, we hear recently, or whatever. In order to address some of these things, the community has come up with other techniques like sophisticated cross-validation techniques or the use of holdout sets for checking conclusions that you learn on training data and validate them on the holdout set. People do things like pre-registering the hypotheses that they're going to test and so on. But most of the theory is actually for the static case when sort of the questions are all known in advance, they're fixed. And science is by nature an adaptive process. And this famous statistician, Tukey, said that we often forget how science and engineering function. Ideas come from previous exploration more often than from lightning strokes. In other words, the second question you ask does depend on the outcome of the first question. The second study or the kth study that you run depends on the outcomes of the first k-1 studies. It's fundamentally adaptive. Moreover, in some sense, it's going to get worse. Normally, what you would do when you want to have a new study is you'd go off and you'd recruit a new data set and work on the new data set. You'd have fresh samples. But what may happen now instead is that people will be working with some canonical data sets, some canonical, very, very large data sets. And it won't be feasible at all to go out and recruit another fresh set of data. Just absolutely not possible. Everybody will be working from the same set. So it's a sort of accuracy problem in the land of plenty. We had privacy in the land of plenty where we had good answers. This is an accuracy problem. So let's go back to our formulation. What are we worried about? Here's how we started. In a very formal way, the analyst asks a question from the database, gets an answer, asks another question, gets an answer, and everything was adaptive, is adaptive. So the question that's asked at the ith step depends on the previous I-1 answers. Our worry is that the analyst will find a query for which the database is not representative of the population. And will say, hey, I have this great new discovery. It's something that has been overfit to the actual data set. And what we argue is that differential privacy actually neutralizes the risks that are incurred by adaptivity. In other words, in our way of thinking, it's hard to find a query for which the data set is not representative. And I know that's confusing, and I'm just going to give you a little bit of intuition. It's the end of a long week. So let's fix a query queue in advance. No data have been collected yet. What fraction of the population is over 6 feet tall? Now you're going to go out and you're going to sample the population. And you're going to come up with a pretty big sample. And you know that almost any big sample is going to give you a good estimate for this. That's why statistics works. So in our language, most data sets are representative. Most large data sets are representative with respect to this query. Go out, find a data set, you're likely to get a good answer, an answer that's representative of the population as a whole. Now suppose in the process of adaptive exploration, the analyst came up with a query for which the data set is not representative. Then in some really concrete sense, she learned something significant about the data set. If it doesn't happen when she didn't already interact with the data set, and it does happen when she does interact with the data set, then she learned something from the data set. Something has changed. So very intuitively, preserving the data of the privacy of the data may prevent this kind of overfitting. And that intuition turns out to be correct. So there are known connections between notions of the stability of a learning algorithm and its ability to generalize. I mentioned this very early on when we were just defining privacy in the first place and saying why our notion might give us utility. And the stability notions that were considered in prior works don't compose, but differential privacy composes. That's, as I said, that's where all of the power is. So this gives us a calculus or a toolkit for building up complex algorithms that satisfy stability guarantees that turn out to be sufficient to give generalizability. Now, if you present this to someone who works with data, they'll say, okay, get lost. We have our way of working with the data. We don't want to do anything in a differentially private fashion. Vanessa knows this is true. Down with differentially private interference. Okay. So our answer to this is, go ahead, make my day. So what do I mean by this? Say, work on the training data set the way you have always worked on training, on your data. So take your data, randomly partition it into holdout and training, and then do everything you used to do on the training set, just as you did before. But when you think you've come up with an interesting conclusion, you are going to test it on the holdout set the way you've always done before, except not. You're going to interact with the holdout set in a differentially private way. So learn on the training set, check against the holdout via a differentially private mechanism. And the key point here is that what you can argue is that differential privacy ensures that your future exploration, maybe the holdout set says, yes, you have a valid conclusion. Maybe it says, no, your conclusion is nuts. Either way, if you went back to the holdout without having used differentially private access to when you go back to your training set, if you had not used differential privacy, then your questions have been contaminated by the holdout set, and they won't be independent of the holdout set. What differential privacy does is it essentially says, if you've accessed the holdout set in a differentially private way, then your subsequent queries are intuitively, roughly speaking, independent of the holdout set. So you can use it again. It's a reusable holdout set. The ability to reuse is new. How would we do it? Well, one case that we've analyzed uses statistical queries. Again, those counting queries, how many people in the database satisfy property P. And you guys know from the learning theory literature that statistical queries are very powerful as a learning mechanism. And we're going to our interaction with the holdout set will be through the sparse vector technique that you've heard about. So when you think you found something interesting, some predicate that's really interesting, you estimate, you compute what is the fraction of the training set that has that predicate, and then you go and in a differentially private way, you learn what is the fraction. You learn whether the difference between the fraction on the holdout and the fraction on the training exceeds a threshold, whether the difference exceeds a threshold or not. That is a sparse vector question. And so you can officially handle exponential in the size of the holdout many queries, tolerating up to the square of the holdout set size of failed validations. Okay, so in conclusion, privacy-preserving data analysis is a problem that's been studied for at least 50 years. Differential privacy is a general solution concept, and it's robust to the networked world. There's a lot of work going on in different areas, programming languages, formal methods, signal processing statistics, blah, 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 even law. And as of this time, there is still no competing theory of privacy-preserving data analysis. But the approach also tells us something fundamental about computing with stability. We have a general technique for statistical validity in adaptive data analysis, and we've seen that it's also being useful in other fields like economics and game theory. So it is talking about computation in some deep way, and it's very exciting to me to try to understand that.
So this is more of a comment. And you're picking the most popular hobby model. I don't think it's actually that unlikely that the wrong one will come out on top, because if the noise is independent for each respondent, then the noise standard deviation is on the order of root n. So
Actually, no, it won't be on the order of root n because we're using the Laplace noise, and the Laplace noise is being scaled to 1 over epsilon, or you can think about it in terms of the exponential mechanism. So what happens is if there is a decent gap. Look at the...
sounds pretty scary as well, right? If epsilon's really small.
Epsilon is really small. Yes, nonetheless, we tend to think of epsilon as a constant, and we tend to think of n as very large. We usually think in terms of internet scale data sets, but you're right, with small data sets, it would the noise could be very bad. And the specific bounds you can get from the exponential mechanism. Like, even if you don't get the very best, you might get one of the most, a hobby which is among the most popular. If there's a big gap between some popular-ish ones and the others.
So the lower ranking hobbies, though, right? It would, you know, it would really, you can't rank the less popular hobbies this way, because then.
So this is just a technique for answering what is the most popular. There's quite an interest in saying what happens, what about top K? And I can refer you to a paper that talks about that. But typically you'll end up paying the square root of K factor for that.
So Cynthia, I know you're interested more in like politics and what's used in the real world right now. So do you think the differential privacy is having, or is close to having, the impact that you would like to have? So for people to change their ways, or I don't know, what's the status?
What is the status? That's a really good question, and I'm not current on everything. But I would say there's this sort of wave happening of more and more people who are getting to the point of implementing or trying to implement. So we're sort of on this uptick right now. And I don't know what's going to happen. I simply don't know yet. Well, I mean...
Is there a possibility to apply differential onto some probabilistic database? There are some randomness on the database itself, not only the approach.
I'm not sure. I'm not sure exactly what you mean by.
For example, the probabilistic database. I mean, each entry has some certain probability to be correct.
So, differential privacy is a worst-case guarantee, which means that, however it is that you get your data sets, it still works. And so, if they're probabilistic, it'll still work.
So, for example, on top of like Markov chain stuff, so we have a probabilistic prediction on the next step, and in this case, I mean, can we apply DP on it?
So, if I understand your question correctly, which I'm not sure of, I think the answer is yes. Guy, do you think the answer is yes?
What was the question?
The question is, what if we have some randomness on the database or data set itself?
So as Cynthia was saying, the guarantee of differential privacy is a worst case guarantee. It doesn't matter where your data is coming from, differential privacy works. Perhaps what you're asking is, can you use the noise that's inherent in the data from the generation process in order to get privacy?
I have one comment about that. So Abhishek Abaumek and I looked at the question of whether you could use database churn. So people come and they leave from the database, and that provides it provides some uncertainty if you assume that the adversary just can't know who all is joining and leaving the database. They could know something, but not too much about it. And it's unbelievably worse than you'd think it would be, unfortunately. Maybe other people can come up with better models of churn that are still realistic, but give better bounds. But unfortunately, the results were quite negative.
Maybe I'll just add, because it came up before, I think the difference from correctness is that here you are, as in cryptography, we're thinking about an adversary who's trying to learn something about you. And this adversary might go to some lengths to understand more about the process that the data came from than just what your model is guaranteeing. So, we really are thinking about adversaries as we are in cryptography, and so it's hard to just assume that the data is random and no one knows, people know very little about it. That's, I think, where the hardness comes from. No?
It was just really awful, even without anything that complicated. Shai?
Does differential privacy have a way to guide the statistician in the process of collecting the data? So
Did you say of collecting or correcting?
The statistician starts from something that he wants to study and a whole world of populations there to choose for in order to collect the data for studying that problem. Are the differential privacy tools useful for in that aspect of where do I go to collect the data for my study?
I don't know the answer to that question. Differential privacy is something that we use on a data set. So
you could think of the entire universe as your data set now, and then there's something about which, where do you access it, maybe. I don't know.
It's a very intriguing question. I'm sorry, I don't know the answer. Guy? Any? No.
Oh, that interesting.
Very interesting. Any other questions?
I was going to ask a question about bootstrapping methods and differential privacy, but I see that Adam Smith has already written a paper about that. So I thought kind of the approach of applying differential privacy for hypothesis testing is something that, under the assumption that bootstrapping is differentially private, is in fact something that gets done surprisingly often in analysis of data in the physical sciences.
So I don't know. I guess this is a comment and not a question. But
question.
Right, okay. Right. So it sort of passes close to two things. First of all, the question of whether you can do differentially private control of the false discovery rate is a really interesting one. And recently, Weijiasu, Li Zhang, and I came up with such an algorithm, which, to our knowledge, is the first such algorithm. And I'm pretty excited about it. But so that's something on false discovery. But on the bootstrapping, this is not a heuristic. This is a real algorithm with real provable FDR control guarantees. The bootstrapping, I think we're going to see more than just the first paper from Adam. I'm glad he wrote it, but I think that this is really interesting, and there are some variants that you might want to do, like bag of little bootstraps, that could be very cool in this context. But I've been working on that recently with, oh God, terrible to blank on your co-author's name. Can you help me? Do you remember? This summer, this past. Okay. Anyway, sorry. Anyway, it's very interesting, and I look forward to lots of people looking at bootstrapping in this setting. Absolutely.
Well, in that case, the follow-up is I'm quite curious what your current work/results on applying.
Since we don't have a proof yet, we just don't have. I can't call it a result, but I'm looking forward to that.
So let's thank Cynthia again.